So, hello and welcome everyone to my presentation on the numerical modeling of hydrogen embrittlement of pipeline steel. And wait a second. Yes, it's working as intended. So my name is Niels Schultheiss. I'm a PhD student at RWTH Aachen University in Germany. And as you all know, there's a rule: if your research facility is dealing with metallic materials, there has to be at least one researcher dealing with hydrogen embrittlement. This is why you and I are here today. My topic today is the numerical modeling of pipeline steel with hydrogen embrittlement on a component scale. You're fully aware of the motivational background behind this. There's the idea we could use the natural gas structure, pipeline structure, to transport hydrogen. And for that, my research goal is to find a computational efficient continuum damage mechanics model that is able to predict the altered mechanical properties of the pipeline steel on a component scale. So in comparison to the previous speaker, I'm looking for a model which is able to predict the material behavior on a large scale, like an entire pipeline section. Yes. And for this, I'm going to combine two already existing models, and I will present the combined model and its key ideas. So let's talk about the mechanically coupled hydrogen transport model. This model has been recently published by Andres Diaz. And as you can see, this hydrogen transport equation looks very similar to the one we just saw. But there's one key difference. This is dependent on the chemical potential. And this yields one great advantage. We do not longer need the gradient of hydrostatic stress. The gradient of hydrostatic stress is very hard to compute in abacus explicit. And why do we want an explicit solver? Because later on, we're going to introduce our material model, which is coupled with damage. And this will introduce very high degrees of nonlinearity. So we are interested in an explicit solution. Also briefly mention what is actually hydrogen transport within the material in this context. It's just the uptake of the hydrogen from the environment. And then it's the normal lattice diffusion, which is influenced by the hydrostatic stress, which is commonly agreed upon. And then also we have increased hydrogen at dislocations, and maybe the dislocations can also transport the hydrogen. So the key assumption of this model right here is that only this diffusible part of hydrogen contributes to the hydrogen embrittlement. We are not considering strongly trapped hydrogen and other defects. Yes. Also, we are not directly modeling dislocation density. We are just considering the plastic strain. So dislocation density is a function of plastic strain, as you can see here, which was taken from the literature. Yeah. We are moving forward to the continuum damage mechanics model. This is the modified binary splitting model we are very familiar with at our research lab. Our damage mechanics models always consist of two parts. One is plasticity, the other one is damage. First, the plasticity is dependent on load angle. Load angle is in reference to the third invariant of the deviatoric stress tensor. And on the right-hand side, you can see how this alters the shape of our flow potential or yield surface. It results in this Tresca-like but smooth and differentiable yield surface. Yes, and here are the according equations. There's to note we're still using an isotropic Hardy function. Yes. So let's move on to the damage part of the model. On the right-hand side, you can see if we are not considering damage, we are overestimating the stress response of the material. And we are considering two key points. One is the damage initiation, and then the other one is the fracture. In between those 2 points, we have a damage accumulation function. What is the idea behind this? What is structural damage in this context? It's just the process of void depolation, void growth, and void coalescence. As soon as we hit this criterion right here, we will decrease the stiffness of our matrix until it reaches 0, a critical value, and we can delete our element. And those criterions are dependent on stress triaxicity, load angle, and equivalent plastic strain. Thus really covering the whole range of every possible stress state. Those are the corresponding equations I just showed you. The equations for the loci are the same, they're just dependent on different parameters. And this is the damage accumulation function, strongly dependent on the energy release rate. And the whole model will be calibrated based on experiments. So what we're doing is we're doing tensor tests on samples with different stress states. We'll take the critical stress states and transfer it to those loci. All right, now that we know the basics of the two models, we are going to combine them in one. So we can consider not only the complex stress state, but also the local hydrogen concentration, because the base assumption is always that the degree of hydrogen embrittlement correlates directly to the local hydrogen concentration. And I will just go over this very briefly. Here in the top, you again see the transport function I described in the first model, which will give us the total hydrogen concentration. And after that, those are the formulas you just saw. And now as you can see, hydrogen embrittlement basically affects every key component of material behavior along the way. And before I go into more detail, I will take a quick step back and talk about the hydrogen embrittlement mechanisms again, just to show you that the implementation I just showed you does not directly model those mechanisms, but does attribute them and incorporate the physical meaning of them already. So as you all know, there are two key hydrogen embrittlement mechanisms. One is HELP, the other one HEDE. Let's talk about HELP first. HELP is hydrogen enhanced localized plasticity. It acts more on lower stresses. The key idea is that hydrogen traps at dislocations and maybe moves alongside them. And then we have a higher hydrogen concentration in areas of high plastic strain or high dislocations. And this causes usually lower your local yield strength, but also a decrease in hardening behavior. And due to this HELP mechanisms, there are other mechanisms which are strain-based dependent. The other one is HESIV, hydrogen-enhanced strain-induced vacancies. The idea is that hydrogen promotes also the nucleation of nanovoids. So it's also directly linked to something what we would consider a ductile damage mechanism, which is mostly driven through strain. So the key idea is that we have to put constant plastic work into our system to drive forth our ductile crack propagation. The other one is aid. The idea is that it promotes dislocation emission on the surface, so it eases the hydrogen uptake in areas of hydrostatic stress. And on the other side, for high applied stress or high concentrations, we have the HEDE mechanism, which is associated with a sudden catastrophic failure, a decohesion, and a very rapid loss in ductility. And now we're coming back to the implementation I just showed you. And we can see that all the ideas of those mechanisms are already applied or incorporated in the model. First, you can see here this boundary condition, which holds true for an in situ setup, considers the ate mechanism because we are increasing the hydrogen uptake in areas of high stress. Then we are considering the effects of it, right? It's always about the effects, not the mechanism itself, because we are on a macro scale. We are lowering local yield strength based on local hydrogen concentration and also lowering the hardening behavior. And lastly, our ductile damage initiation starts earlier. Also, this is stress dependent. So the locus I showed you earlier might change its shape. So this is what's in line with experimental results. We can see ductile damage initiation starts earlier. Same for the whole damage evolution, the decrease in stiffness, and thus lastly the ductile fracture, which is for a basic tensor test. This would give your fracture strain. What I did not mention is we could also incorporate a brittle fracture criterion, which would be mainly driven as a stress-based criteria in contrast to those strain-based criteria. And the idea is that the local critical cleavage fracture stress is also a function of local hydrogen concentration, lowering this critical value, and thus incorporating also the ideas of the Heger mechanism. And the beauty of this model is that it would, to some degree, dynamically incorporate all the effects at the same time because they're solved on a element basis. Yeah, that's really the key aspect of this model. However, we are really in early stage development. We just started working on this. We can increase the local hydrogen concentration on a component scale. However, it does not work as intended. Just the original model is working very well. And now I already come to the summary because I really would love your feedback on this idea. So what have we seen today? We have a chemical potential-based hydrogen transport function. This leads to an underload to an inhomogeneous distribution of local hydrogen concentration. And afterwards, we're going to link all our failure criterion or plasticity criterions to this local hydrogen concentration. Yes. Then thank you for your attention.